everyone, welcome back to SAT Math Question of the Day with Professor Emeritus Seth Chaiken at University of Albany and Joel, Seth's brother. We're here to try to help you understand how to do SAT math questions, maybe even all types of math questions. This particular question is from Khan Academy, and Khan Academy offers free practice on all the topics that are on the post-2016 SAT. The Khan Academy splits up the practice into 40 different topics. All 40 topics can be on the SAT. This is called data collection and something else, I think analysis or something. And we're starting here on the first question. Khan gives you 4 levels, 5 questions a level, total of 20 questions. Normally we start at a higher level, but these questions are very different because you don't usually get these questions at school at all. So we're starting at level 1, and if these are too easy, maybe we'll blast through 5 of them, but we'll evaluate later whether we should do more today. Okay, so please read the question and do your best, and then come back and we will discuss. In a recent random sample of Louisiana residents, 34% of the sample identifies Black or African American. Based on this information, which of the following conclusions is valid? So in these questions, you really have to use common sense, and I think you also, the operative word here is which is the best answer. I think that's the way you have to approach these things. Which is the best answer? So let's see.
Well, third is you need to read the data in the question and the proposed answers word by word.
And you have to read all of them. All the answers.
Well, I think that may not be as necessary, but when you consider one of the answers as a possible answer, you must read it word by word and think about what the words mean,
Okay,
and then connect it with common sense.
Now,
to what the meaning of the question was.
On the other day, we realized it's also real important when you have SAT math questions to invest a second or two to decide if there's a real quick way to do it, like using some sort of pattern or trick. I think in these problems that doesn't apply. I don't think you can see, there's this super fast way of doing it. There's really only one path in these types of questions, which is to read the answers carefully. Read read everything very carefully. Very carefully.
Yeah.
Okay, so let's go. Let's see if we could do it. Okay, so 34% of the sample. Oh, that's important, right? It's a sample. They didn't do every person. They did only a sample, right? Okay.
That's right.
Exactly 34, but that's crazy. No, it can't possibly be right. Exactly, that can't be right. Exactly 34 people. What?
Okay, the question is not whether it's possible. It's not asking whether the situation is possible. It's asking whether the conclusion from the data is valid.
Right. So it looks like every time you have a study, exactly doesn't really work. It's certainly not the best answer. This is possible. It's certainly possible, right? That it's possible that about 34%, it's a possible answer. Now, what about this one? The percent of Black Americans cannot be estimated from the given information. So it looks like it's between those two. Do you agree?
Okay. Yes. Yeah.
Okay.
Yeah.
So
yeah.
I guess we could cross these off. Okay. Now, if it's a small sample, then this can't. They don't tell you how big the sample is.
But they told you. They told you that the sample was recent and that it was random.
Oh, and it says based on this information.
And it's based on this. So the question is, what conclusion is valid?
Right.
Based upon this information.
Right.
This information is that the sample was recent
right?
that it was random, that it was a sample, it wasn't a selection,
Ooh, okay.
right? And
Right,
that of the sample, 34% were counted as or identified as Black or African American.
right, right. So then you are saying it's C.
I would say I would pick answer C. Yeah, it's the best answer.
I would have to
You
agree.
know, we would trust that the sample that the statistical measurements were done in a competent manner, that the sample was large enough
Yeah,
so that there would be a high probability that the estimate from the sample is close to population,
yep,
the population percentage.
yep,
And also another assumption is there's a difference uh, being between someone who, say, participates in the study, being Black or African American
mm.
versus identifying
Oh
as
yeah,
Black
yeah, yeah,
or
yeah, yeah, yeah,
African
yeah,
American.
yeah, yeah. You're right. Yeah,
And indeed, these say often questionnaires about this kind of thing will have a choice where of you decline to report,
mm.
right?
Yeah,
But again, there are assumptions that we make when we do statistics that give us not 100% reliable judgment
yeah,
of reliability of the statistics.
yeah.
But again, the SAT questions are posed in the form of picking the best.
Absolutely. The operative
And
word.
I think it's pretty
Yeah,
clear that for various possible failures, uh, answer C is the best of the other. It's
right.
the best of the four.
So the approach on these questions is a two-pronged approach. Read the questions very carefully, read the choices very carefully, and choose the best answer. That is really how
Yes.
you approach these things. Okay, so let's see. By the way, the SAT people did not write this. The Khan Academy people wrote this. I wouldn't be surprised if the SAT people wrote it. They would have changed this to be as identify as, because their SAT people are probably
Yes.
more careful in writing questions than Khan.
Ah,
Okay,
yes, quite
so
true.
let's see. I have to stop the annotation. Let's see if we are right. Can't wait to see the
No,
fireworks.
let's see what their answers are. Let's
Of
see if
course.
if if
Okay.
our answers agree with their answers.
Okay. Check answer. Yes, we get the fireworks. Now what we do is we clear our annotation and we look at see how they did it. Oops. Okay, let's see how they did it. We can use the information from a random sample to make inferences about the population for which a sample is drawn. Sample is right. Okay. Um, we annotation clear all. Okay. We can extend that same statistic to the population. Okay. And it says a little note. Note population inferences we make are almost never exact. Right. That's why the exact answers are not the best answers. Okay. So that's it. Right.
Right.
Clear all drawings. And then we go down. And that's it. Okay. My attitude is we should let people finish the practice themselves and not do the other four in this set. Because these questions are different from the others, and I think we should stop here. And maybe in a few weeks we'll do the next one, because we're going to be going to all over all these topics. We're just going to be mixing and matching these things, mixing these up. So I think we're done.
Okay,
Okay.
we're done. Thank you.
Yeah, we're done. We're done with this.
Goodbye.
But now it's time to feed the Seth a question. But
Oh,
if you don't feel like staying, that's just totally cool. Please like us, dislike us, give us comments on our YouTube videos, or email us at satmathquestion@gmail.com. And if you have any math SAT questions you want us to go over, email them to us at our email address, satmathquestionoftheday@gmail.com. Now it's time for the special feature of Feed the Seth. So this only happens when real tough questions come up. And I've been meaning to ask Seth this question for a while. Why? And I have some. Why is it that it seems to me that the human brain it's easier for the human brain to do problems in a forward manner than in a backwards manner. In other words, it's easier to multiply 3 times 4 to get 12 than it is to say what times 3 equals 12. It happens a lot. You see it. Let's say when you have the area of a triangle. Okay, area of a triangle is 1/2 base times height. Base, height. It's very, someone tells you the base is 3, the height is 4, what's the area of the triangle? But very often, if you're told that the area is 24 and the base is 3, what is the height? That sometimes really confuses people. What do they do? Why? And I have a specific example which totally threw me, I have some thoughts about this. It's a backwards probability question, which for the life of me, there's no way I could have done it. No way I could have done it. And then I realized, this is a backwards question. Maybe my conclusion is that people can do backwards questions, then they really, really totally understand the forward question. But have you noticed this, that the backwards questions have thrown you or throw people? And do you have any thoughts about why the human brain has a trouble doing a problem that's backwards as opposed to a forward question? And do you have any idea what I'm talking about?
Well, my response is that in computer science, we study that question. We study a question like that. We study questions like that, except we seek answers about how and why computers are found, how and why it seems that computers need more or less time to solve different kinds of questions.
Okay.
And there is it's a key, very big, a very big, wide-ranging kind of problem. And then one important case of it remains one of the big unsolved questions in computer science. And that is the question of whether you could look up on a search engine, try is NP equal to P?
Okay.
And so let me describe what that question means. An explanation of that question, in the form of asking it about people.
Okay.
Okay. So it goes like this: what's easier? What is easier? Say if you're given a recipe for calculating an answer from input numbers.
Okay.
So you start with the input numbers and read the instructions of what to calculate, and then get an answer and check against the proposed answer.
Yeah, so
and check that it's right.
That's this one here. Calculate area.
Yeah, it's even easier. It's a question: is given the triangle, and you know that the height is 3 and the base is 4. Is it true that the area is 6?
Yeah. Okay.
Okay.
Yeah.
Now the other kind of question is. Here's the kind of question. You're given the triangle, you're given the way to compute the area, and you're told that the area is 6, and your job uh is to guess or find out if there is a solution, and then verify that the solution is there. But you're not told what the solution is.
Okay. Right. So there's
And the
different
thing is,
possibilities.
when those two kinds of problems uh, are scientifically formulated so that they become problems that it makes sense for a computer to work on,
Right.
computer scientists cannot yet explain why it seems that the first kind of problem, where you verify a proposed answer and you verify proposed numbers that the calculation leads to a given number, versus guessing a proposed answer and then verifying it. With is computer scientists do not know whether, first of all, they do not know whether they do not know for sure scientifically whether computers, in a certain sense of how fast they operate, called polynomial time, whether computers inherently can only solve the first kind of problem fast and not solve the second kind of problem equally fast.
Wow. 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 Wow.
And the thing is all of our experience is that it coincides with what you observe, what you say about people, that the second kind of problem, the reverse kind of problem, is harder.
Yeah. Yeah.
Yeah.
Wow. No, that's
So there's something behind it in terms of present theories about what computers can do.
but
Now,
so
with respect to people,
yeah.
I would say it's related to the question. Suppose you have I don't know if it's old fashioned, a combination lock,
Yeah.
or perhaps you've put a pin,
Hmm.
per a secret identifier to unlock your phone.
Right.
What is easier, to unlock your phone when you know the pin, or to unlock your phone when you don't know the pin?
Well, obviously, when you know the pin.
Yeah. Now,
Yeah.
when you know the pin, yeah, you put the pin in, and the phone does a calculation
Right.
to get it to unlock itself,
Right.
right?
Yeah.
If you don't know the pin, uh, the what you can do is try to guess,
Yeah. Yeah.
and what you can do is unless the phone is built so that it limits the number of times you could try, you could exhaustively try all the possible pins,
Right.
or try pins at
Yeah, but
random
that's a different
until you
problem.
find one.
That's a different problem. But let me show you a specific
But the
example.
thing is, it's yeah. Now the thing is, in mathematics, there are some problems which are called invertible problems, where as a result of a lot of history of mathematical exploration and discovery, that people have figured out ways for certain problems of doing a calculation, that solves the inverse.
Yeah, yeah, yeah. So they're right, exactly. Three
Yeah,
times
yeah,
four
yeah,
is 12, and then 12 equals 3 times what? That's an invertible. That's an
yeah,
invertible question, right?
yeah,
So Let me show
Well,
you.
here's a case that's of critical uh, that's made use of in a lot of technology today. It's a question of, given uh, a number that's not prime, find uh, since it's not prime, it has at least two different non-trivial factors.
Okay.
At least two different numbers that are not equal to one and are smaller than the given number. That you multiply them, you
Right.
get the number. Okay, if you're given the two factors, it's easy to multiply them.
Yeah.
And check that you get the number.
Right.
But if you're not given the factors, well, for small numbers, it's fair. You could just count up. You just check about up to the square root.
Yeah. 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 Yeah.
But if the number is a few hundred digits long,
Right. Yeah.
It appears people, at least in the unclassified information of known to people, don't know a fast enough way of guessing the factors of a large prime number.
Yeah.
That makes it possible to do it in a reasonable amount of time.
Right.
Even with the biggest computers, most powerful computers in the world.
I know. Okay, but we're going a little off.
So the point is that problem, the fact that the factoring problem appears to be much harder than the multiplication problem, is a basis for trusting the security of many of the systems of encryption and digital signing that's used all over the world today.
So, right. Okay, so you're talking about how in the extreme, the backwards problem is so hard that it's used for security. But also, we're talking practically, forget about really hard backwards problems. We're just talking about regular backwards problems that throw people. So let me show you an example of a backwards problem.
But the thing is, it's pretty clear. It's pretty clear that if you survey all of the systematic methods of solving problems, the methods for backwards problems have more steps.
Right.
Than the methods for forward problems.
Okay, right. And things with more steps are more complicated.
Yes. Okay. You do this. So I'm not talking about the question of figuring out what the steps are. For those problems for which people have figured out solutions in terms of steps, we have observed that many reverse problems have the best solutions are a lot longer than the best solutions for the forward problems.
And the insight
now, the question is, why is that true?
Well, okay.
And why is that true?
Yeah. Okay.
And computer scientists relatively early in the history of computer science, but fairly late in the history of science, these kinds of investigations began a little less, about 100 years ago.
Okay.
Roughly 100 years ago, did people begin seriously asking these questions. And when the question was formed in a precise enough way to be called scientific, the answer is we don't know.
Okay. Interesting.
What we do know is that there's a class of problems. We do know this is the undecidability results. that for that there are some extremely difficult problems that uh that can be proven, if for which it can be proven that when the problem is formulated scientifically enough so that a definite answer can be uh, scientifically verified, that is a proof, we can prove that some problems computers cannot solve.
Okay.
That's called the one of those problems is called Turing's halting problem.
Okay. Okay. Before we get too deep, before we get overboard here, let me show you an example which comes from a upper level high school class in probability, where
Yeah.
you have to really understand the forward problem to be able to do the backwards problem. Of course, I never really understood. I'm not great on probability. So this problem completely floored me, and I realized this morning that, oh, it's a backwards problem. Actually, I probably realized it a few days ago. Then I realized, oh, the reason why I find this problem virtually impossible for me to have done without looking at the answer was because I never really understood the forwards problem. So, can I show it to you, Seth? Seth's pretty good at
Sure, let's
probability.
try it. Yeah.
Seth's pretty good at probability. So let's see how this works. I guess here it is. Let's see. What do I do here? First of all, I kill this, and maybe I go like that. Maybe I go like this. Ooh, it's hard to see, right? Um, ooh, I don't know. Can you see it, Seth? It's probably really hard in the. Oh no, maybe in screen share. Oh no, you can't see it in screen share. Okay, let's do a screen share. Here we go. Screen share. Now, you probably can't see this. It's too small, right? Seth?
Oh, I get close enough. No, no, I can't.
Oh boy. Oh boy, boy. What are we gonna do? Uh, I know what we're gonna do. We're gonna stop the share. No, we can't stop the share because Seth needs to see it. Uh, oh.
There you go.
Yeah. But I have to go down somehow. Oh wait. Wait. Hold on, everyone. Hold on. There we go. There we go.
Okay.
Now we're gonna make ourselves small. Okay. I know everyone likes looking at us, but we're now very small here. Okay. So here we go. Um, this challenge question here. This is probability for a relatively high level 11th grade math class, Algebra 2.
Oh,
Okay. Um,
oh,
can everyone see it? Henry and
oh.
Gretchen plan to sit outside shooting stars.
Yeah.
Now, it took me a while to understand what's going on, but it looks to me like this is a backwards question. Because what the person is doing is the person solving that x to the sixth equals 0.01 to get the answer. This thing here,
Oh,
this here. So he's back solving. He knows that the final answer was 10% from the problem. He knows the answer is supposed to be 10%. So he's back solving to see what the probability is in any 10-minute period of not seeing a star. So he realizes that the probability of not of x is the probability of not seeing a star. Right, is 68%. So that's gotten through doing it backwards, and then you do the inverse of the complement of that, which means 32% of seeing a star. So it's almost like a backwards problem twice, really, almost. Although, but I mean, this is a hard problem, right?
well, I don't know what is the do they give a principle to apply to solve this with problems like this?
Well, isn't the principle here the given probability, the binomial question, the binomial probability question, given a probability of something, let's say dice
Um,
is, given the probability of something,
yeah.
if it happens n number of times, what's the probability that it will happen those number of times? Um, I mean, is because this thing here. I mean, looking at from the forwards question. This would be the forwards question, right?
Yeah.
If the probability of seeing a star
Well,
is,
I think that maybe is your approach to divide the hour into 10-minute periods.
that's what this person's doing because the person only wants to stay for
Okay,
10
so
minutes.
yes, I think that makes sense. You divide the hour into 10-minute periods, and yeah, and then the probability of seeing at least one star
At least
in
one star.
10 minutes.
Right.
Not exactly one star, but
That's right.
at least one star
Right.
is S.
Right.
Then the probability of seeing no stars, right, is 1 minus S
Right.
in the 10-minute period.
Right.
And so the probability of seeing no stars in an hour, right, is 1 minus S, what, to the sixth.
Right.
And you're told that that's 90%.
Right.
And
No.
so you want to find out what S is.
Right. Yeah. So
you have to take the equation is where's my annotator?
Yeah.
Right. Oh, let me get the equation is S is 1 minus S to the sixth equals 9/10.
Wait, we should write down what S is. We should do a let
Okay,
statement.
S
Let S
was the
be
probability of, right, that you see at least one star in 10 minutes. Okay.
right.
So 1 minus S is the probability of seeing no stars in 10 minutes. 1 minus S to the sixth is the probability of seeing no stars in 60 minutes. And the given is that that's equal to 9/10.
No.
Now,
It's a 90% chance you will see a star
I'm
in
sorry.
an hour.
Oh, you will see a star.
Yeah.
So it's the complement of that.
So then erase everything. Erase everything and do it again.
No, so I changed it from okay.
Oh,
so
right.
this is the
yes,
probability of seeing no star in 60 minutes.
Right. No star.
And that equals 100% minus 90%, which is 10%.
10%, right. Okay, yeah, and that's right.
Which is percent,
right.
which is 1/10. Okay, right. so we now the answer is the answer we want is the probability of seeing a star in 10 minutes, right?
Right, that's right.
So we want to find S.
Right.
So it's an arithmetic. We have to take the sixth root of 1/10.
Yeah, which I do over here. Yeah.
Yeah, which is well, what's harder? The sixth root of 1/10. 1/10 to the minus sixth. No, sorry, 1/10 to the 1/6.
To the 1/6. Yeah.
That's the number which when multiplied by itself, 6 times gives you a 10th.
Right.
Right.
Yeah. So the answer is 0.68. Because he did it. He did it right here. That's what's at the bottom. Look at the bottom of the screen. He did it. X to the 6th is 0.1.
Yeah.
His X is your 1 minus S. Okay. His X is your 1 minus S.
Yeah.
So the answer is 0.68. This is a percent, believe it or not. So this
the answer is 68 hundredths,
Right,
no over
68
68%.
hundredths, yeah. Which means that the 68 hundredths of not seeing a star, so that means 68, yeah.
So 6, yeah.
So then 1 minus that is 0.32. The complement to that is 0.32 of seeing a star. Yeah. So
But we're interested in probability that they actually see a star.
right,
Okay, so the probability that they see a star is the complement.
right,
Is at 0.68, 68 hundredths. Subtracted from 1.
right,
So
right.
it's about 22
Well,
hundredths.
32.
32 hundredths, right?
32% chance
About
of
a
seeing a
third.
star, right? So
Yeah.
the person said,
Yeah.
well,
Okay, so now, and furthermore, let's be more precise. That probability is the probability of seeing at least one
that's right.
star.
That's really an important part.
Not exactly one star.
That's right.
Yeah.
So I mean, I think this is a backwards question. Why is this a backward question? Because the forwards question would be so much easier. Wouldn't the forwards question be, hey, in a 10-minute period, there is a 32% chance of seeing a star. This is the forwards question. In 10 minutes, there is a 32% chance of seeing at least one star.
Yeah.
Okay, what is the probability then of seeing at least one star in an hour?
Oh.
Right?
Right.
And then that would be probably 90%. Yeah. Right?
Yeah.
That would be, what is the probability? Probability of seeing a star in 60 minutes.
Yeah. Well, you reverse it, right?
No, but this would be the forward problem. This would be a lot easier,
Yeah.
wouldn't it?
Yeah. But you would do the you'll be using the same formula, right?
Right.
Using the same principle.
But you're not solving for X, you're calculating.
Yeah.
So this would be the forward problem. This is an easier problem to understand as long as you understand something about probability. I'm not quite even sure I understand this one, but let's see.
Again, I think what I need to do is there are two. You're talking about two rather different things. One thing that you're talking about is figuring out a way to solve the problem.
Yeah.
The second is that having figured out a way to solve the problem, which would result in a step-by-step procedure that tells you what arithmetic to do.
Yeah.
How hard is it to do the arithmetic?
No, I mean, no.
No, they're different kinds of things.
No, all I'm trying to say is that if you formulate the problem, if you formulate this situation in the forward way, it's easier to understand what to do than to do
understand what
way.
to do is figuring out a way.
Yeah.
Right. Well,
no, but I mean, in this sense, you have to, if you were to do the full problem here, you have to understand to break the thing up into 10-minute periods. If you formulate the forward problem, it already is broken up in 10-minute periods. You don't have to have that special insight. It says in 10 minutes there's a 32% chance of seeing at least one star.
You're given the setup for
right.
Yeah, so the problem comes. Yeah. So it comes with this. It comes with. Yeah. I see here. So it's given the setup is the setup that leads to the formula.
Right. It's already told you to break it up.
Is told to you in the problem.
in the forward, what I would call the forward
Yeah,
problem.
in the forward
I would call
problem.
this the
Whereas
forward problem.
in the reverse problem, it's your mystery to find the setup, which when operated forward solves a problem, which is not the problem you're given, but the given problem, is of the form to find an input so that the forward solution gives an answer to the forward problem.
Yeah.
And then you solve it by writing it in algebra, which makes the arithmetic for doing the inversion easy to calculate. Yeah. It's like, I think it is similar to, what's easier to open a combination lock when you know the combination versus when you don't know the combination.
Yeah.
Why is it that it's easier to do things when you know how to do them?
Right. Why is it easier
versus
I guess
when you don't know how to do them?
I guess because it is, right? I mean, yeah, you're right. Here the setup is given to you. So you just have to know how to do this problem, the problem that I circled in black. You have to know how to do that. But my argument here, let's be reasonable, and that's combination lock is sort of a crazy example. It seems to me, my takeaway from this is that in order to do the harder backwards problem, you really have to understand. You have to have a deep, intuitive, complete understanding of how to do the forwards problems. And if you don't, you really can't do the backwards problems. Okay, and this was my strategy. My problem here is I never really
people acquire skills in different ways, and get many school problems. Somebody else centuries ago figured out how to solve the problem. They keep teaching it to their students throughout the generations, and they teach it. And you could learn it, you could learn it in a manner called rote, where you don't understand what you're doing.
Yeah.
But does it mean you solve the problem?
Yeah, I guess, yeah.
When this problem is solved by a computer, does the computer understand how to solve the problem?
No.
But many people carry on activities that they've been taught to do by rote.
So here's a practical suggestion as to what to do when you're stuck with a problem that seems particularly hard. Like I read this problem, I had no idea how to do it. Maybe that's a clue that it's a backwards problem. Maybe when you're doing a problem and you look at it and you say, oh my God, maybe it's a backwards problem, and maybe what you should do is play with it and make up an answer. Maybe you should make up an answer, say, okay, we only have 50% chance. Maybe you should take this 15% chance and turn it into a forwards problem. Say, okay, well, if there's a 15% chance in 10 minutes, then what's the probability of seeing it in an hour? And play with the forwards problem, or maybe, first of all, look at a problem and say, this is really hard. Ask yourself, maybe it's a backwards problem. If it's a backwards problem, play with the possibility of a forwards problem. Make up an answer to the forwards problem. They call this, some fancy SAT books or other books, they call this, oh God, what do they call this? This sometimes happens with percent problems. It's not guess and check. I guess it is guess and check, where you guess in a percent problem. Sometimes the percent's really hard. You guess the answer and then you check it. And that's really taking a backwards percent problem, turning it into a forwards percent problem, and just trying all the different answers. And that may be the way to handle a problem, but the dead giveaway, if a problem is backwards, could possibly be if it looks really, really hard.
Well,
So maybe people can. I think I'll be
Well,
thinking.
that makes sense.
That
That
makes
makes
sense.
sense.
Yeah,
And what's helpful to know about in life is, well, that principle that uh, if you're puzzled about, say how to predict something, uh, a strategy. Yeah, it makes something. That's a very good idea, Joel. Very good idea. That if you have if you you know uh, don't see a way that the information you have leads you to an answer, a way to explore it is to pretend that you have an
that's right.
answer,
Guess an answer.
and
Right.
use, or perhaps even guess
Yeah. Guess an answer. Yeah.
a tentative
Right.
answer, and
Exactly.
then
That's right. Work.
and
Right.
then do math
Right.
to
Go
see what
forward.
happens
Yeah.
with it.
Right. That's right.
And then upon doing the calculations of checking to see if you were lucky, might lead you to a strategy for finding,
Yeah.
a, for making a better guess.
Right. Right.
And indeed, there are, methods. Uh, mathematicians know and teach and invent what are called numerical methods for solving equations.
Yeah. Right. Yeah.
Which work that way. Most numerical methods for solving equations do not work by calculating an inverse function.
Right.
And in fact, the calculations in, say, inverting systems of linear equations are unstable.
Yeah.
So it's better. It's actually better to use a method of calculation where you start with sometimes even an arbitrary guess, and then do a calculation, and the calculation tells you a certain amount to change the guess.
Right.
Where the amount to change the guess is not going to bring you right onto the exact answer, but will bring you closer to the answer.
Right. Yeah. 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 Yeah.
And then you redo the guess.
Right. It's called.
You
It's
use
called
the
an.
second, apply the change to the first guess to get a second guess.
Right.
And then the calculation works out. There are certain testing quantities, and the goal for a solution is one for which the testing quantities calculate out to zero.
Yeah. Yeah. Yeah.
So,
We're
for
really
example,
getting much too far into all this, but it's called an
no,
iterative.
this is no. So this is exactly what you're saying. If you're puzzled by a problem like this, this is actually a good strategy. Like this problem, what is the probability that you will see at least one star in 10 minutes?
Yeah.
Given that
Yeah. You guess it.
you
guess
will see the probability of seeing at least one star in 90 minutes is no, in 60 minutes is
90%.
how much? 90%. Right? Well, you say, okay, all right, let's try 10%.
Seth, I know we went through it. We don't have to go through it again. We don't.
I know. No, I'm saying that instead of doing it by algebra, you could have done it where you start with the answer. Start with, let's say, what was the answer? It was like 20.28.
You make a guess, but by making
so
a
you
guess,
make a guess. So suppose your guess is 10%.
right?
So then the probability of not seeing a star
is
90%, right? And
right.
and then raise that to the 6th power,
right?
And see how close you get to 1%.
Right.
You're going to end up getting a lot less than that. than 90%. So you make your guess bigger. Make it, instead of guessing 10%, you guess 15%.
Right. Yeah, you just keep guessing. Yeah.
Yeah, yeah,
Yeah.
yeah,
Yeah.
yeah.
Yeah. Yeah. Yeah. Yeah. Yeah. No, I
But
understand.
and indeed, that is the most problems that are solved. Most problems that are solved in all sorts of computer problem solving in science and technology are solved that way,
Right.
and not by saying, well, the answer is the sixth root of some number, and
Right.
then you throw it
Exactly.
into a
That's
calculator.
right. That's right. That's right. So the bottom line is
And in
though,
fact, your calculator
I know. I
calculates
know. We
the
yeah.
sixth root
I know.
by doing a calculation like this kind I described.
Right. Yes, it's
That's
called
what's done in the calculator.
right. It's called a numerical method, but again, we're the
It's
bottom.
called, yeah, it's
Yeah,
called solving by iteration.
by iteration. Right. Right. Right.
Yeah.
Right. Right. But the big
Well, it's
takeaway.
also it's called, and the in fact so one of Sir Isaac Newton's creations, one of his many creations was the method for solving equations. That way, one of the best is called Newton's method.
Right. But Seth, we're really going much too far. We got to stay
Well,
focused.
that's what happens when you ask the Seth.
That's true. That's
When you
true.
feed the Seth, that's what you get
when
out.
you feed the Seth, you know what you release a wild animal
not
onto
my
the
fault.
world, onto the world. It's not your fault. You're right. I'm sorry. But I think
my fault.
The big take. What am I taking away from this that could practically be used by perhaps a high school student, as opposed to a college student who's doing calculus and numerical methods, is when you're stuck with a problem and it really looks hard. Say to yourself, this may be a backwards question. Let me make a guess to see what I think the answer may be. Do the forwards problem, which is just a bunch of calculations, and then see how close you are to the answer that they give you, and then iterate, and then say, well, I'm off a little bit, and I'll change it a little bit. But by guessing an answer and doing the forwards problem, it'll probably show you how to do the problem in a backwards way. Okay, yeah. I mean that's really the big takeaway here.
Yeah. In high school curriculum, actually, algebra begins. Motivation for algebra is that you could solve backwards problems. How? By posing a forwards problem in which the answer to the backwards problem is a variable x. You write a formula that says formula in x, right, equals the answer to the forwards problem. The forwards problem answer is given in the original problem. And then the motivation for learning algebra is to figure out algebra is a system for calculating and values for x that make the equation true.
Right.
So the whole motivation for algebra is transforming backwards problems into the solution of forwards problems that are expressed with unknowns, right, as inputs to the forward problem.
So in other words, you're saying that it may be true. If every single problem in the world was a forwards problem, there would be no need for algebra. Because you would then plug everything
I think
in.
so. Yeah,
you would plug everything into the formula for the area, and you would never have to solve for anything. You just plug everything in. Life is very easy. You're given three things, you combine them, you get the answer, and you don't solve anything, but you're always calculating. You're always calculating. You're always calculating. Life is easy, and that's like before fifth grade, before fourth grade, you do only calculations.
Well, in fact, I think that's true. That's right, and in the history history of mathematics, the Euclidean geometry of the Greeks did not have iterative methods,
Hmm.
and that led to real puzzles in how mathematics could work.
Well, wow. So
And then as time went by, and even in those times, however, backwards problems are kinds of problems that occur in navigation. And I'm sure, so I would think that people, as they learned, as they discovered over centuries how to navigate on the oceans, they worked out ways of solving backwards problems,
right, because you
which
have to
maybe were not written about as scholarly mathematical scholarship.
right. Yeah, because
Yeah.
if you want to end up at a certain spot, you have to know where to begin.
Yeah.
So,
Yeah. So if you steer, so the question is, which way should you steer your ship?
if you want to end up somewhere 2 hours from now,
Yeah. So you know where you want to end up, but you don't know which way to steer your ship.
right? That's a classic backwards problem.
Yeah. So that's right. So yeah.
So, so I guess we're done. But you can always tell you're dealing with a smart person like Seth when you pose someone a question and their answer is, "We don't know," or "I don't know." And that's ultimately what Seth said at the very beginning when we said, why is it in the human brain, maybe even in computers, are backwards problems harder? And Seth said, we don't know. And that's a good answer because that shows humility and shows it's a complicated question and it's totally a good answer to say we don't know. But it's interesting.
Well, we don't know all the answers. There are questions we don't know the answer to, but there are also questions that we do know the answer to.
Yeah.
The Gödel's incompleteness stuff are answers.
Okay. Well, that's
to a question like this.
But the bottom line is, it is interesting to think about it. It's an interesting observation that the human brain, maybe, I don't know, it's harder. What about nature? Let's forget the human brain. How does nature solve backwards problems? Like, in the forest.
By evolution.
By evolution, which takes a long time, right? Backwards problems are solved by evolution.
Well, when nature, those results of random changes that are better solutions than other results of random changes are the ones that continue.
Right. Also, that's like
right?
an iterative. That's a classic
it's an iterative
method
that's right.
Where something changes and it sees, well, does this get closer to what is optimal? And then the question, of course, what is optimal? We don't, nature figures that out.
Again, it's philosophical. It is. These questions are puzzled over a lot by thinkers and scientists, biologists.
Right.
That's what it all means.
Yeah.
Yeah.
So. Wow. So this really was a very deep discussion. Yeah. So it's sometimes nice to have these, particularly with Seth around, because you can ask the Seth. If anyone has questions, feed the Seth. So we fed you today.
Yeah.
We fed you.
Well, I think I'll take some raspberries. Care for a raspberry?
Literally feed the Seth. Oh, those look good.
Don't drop your.
Those look good. Yeah, those look really good. Nice and red. Yeah.
Very good.
Okay, so some stuff to think about, but on a practical level, when problems are hard, try to do them. Try to guess the answer and figure out what to do, and that may help you.
Yeah.
Okay. Yeah. I guess we're done.
Okay.
Wow, almost an hour. Yeah. Almost an hour today, but a good discussion about this stuff. Okay. Yeah. Tomorrow's Throwback Thursday. Wait,
what's that?
Tomorrow's Thursday. Throwback Thursday. That's cool.
That's tomorrow.
Yeah, tomorrow. Okay, everyone. Have a great day.
Okay.
Bye.
Okay. Bye-bye.